Welcome, and let's talk about SymmetroBloom 4B, a geometric model of 16 symmetries for final term project. So this is a part 5 of our presentation. And again, I'm Jerry Abigail Bakay from BS Ed Math 3A. So for our task 5, show that it is a permutation group. So instead of using this figure or the front part of our geometric model as the original position, we will use this figure. So we just change the symbols to numbers 1 to 8. So this now will be our original position. To get the permutations in this activity, we will perform these moves. So for rotations, we will use rho sub I, and for axes and diagonals, we will use mu sub I. So one way of presenting the permutations is by the use of or by double line notation. So the first move is do nothing. So this is the original and this is the result after doing nothing. So we always start with the result or the right side, no? That's why we have 1:1 here because 1 maps to 1. And then we have 2:2 here. So this thing is the double line notation. And rho sub 0 because do nothing belong to rotation. So again, we have 2:2 here because 2 maps to 2, and then 3:3 because 3 maps to 3, and then 4:4 because 4 maps to 4, and then 5:5 because 5 maps to 5, 6:6 because 6 maps to 6, and then 7 maps to 7, and then 8 maps to 8. That's why we have rho sub 0, and this is the output. And then next, so after rotating the original to 45 degrees counterclockwise, this is the result. So we have rho sub 1 here. So 1:8 because 1 maps to 8, 2 maps to 1. That's why we have 2:1 here. And then 3:2 because we have 3 maps to 2. And then 4:3 because 4 maps to 3. And then 5 maps to 4, 5 maps to 4, and then 6:5 because 6 maps to 5, and then 7:6 because 7 maps to 6, and then 8 maps to 7. That's why we have rho sub 1. So this is the second element. And then we have here rho sub 2. So this is the original, and then this is the result after rotating the original to 90 degrees counterclockwise. So 1:7 because 1 maps to 7, and then 2 maps to 8. That's why we have 2:8 here. And then 3:1. That's because 3:1 here, or 3 maps to 1. And then 4:2 because 4 maps to 2. And then 5:3 because 5 maps to 3. And then 6:4 because 6 maps to 4. And then 7 maps to 5. And then 8 maps to 6. That's why we have rho sub 2. And then we will no longer show one or all the rotations, no, because the process is just the same. So let's proceed to the axis and diagonals. So if we flip the original vertically, this is the result. And as we can see here, 1:1. So 1:1. So or 1 maps to 1. And then we have 2 maps to 8. That's why we have 2:8. And then 3 maps to 7. That's why we have 3:7. 4 maps to 6. That's why we have 4:6. 5 maps to 5. That's why we have 5:5. And then 6 maps to 4. That's why we have 6:4. And then 7 maps to 3. That's why we have 7:3. And then 8 maps to 2. That's why we have 8:2. That's how we get mu sub 1. And then next, I will show another example. Here is the line of symmetry. And this is the result after flipping the original figure. And we get mu sub 2. So 1:8 because 1 maps to 8. And then 2:7 because 2 maps to 7. And then 3 maps to, or 3:6 because 3 maps to 6, and then 4 is to 5, 5 is to 4, and then 6 maps to 3, and 7 maps to 2, and 8 maps to 1. And that's how we get the new sub 2. We will just do the same process for the rest of the moves, and we will get this from permutation. Now, to check if the set of moves forms a permutation group, we will check for closure, associativity, identity, and inverses. So first is the closure. How do we get the elements of this? So first, if we have row sub 0 and row sub 1, we will use permutation multiplication, or one way to check if the set of moves in our geometric model forms a permutation group. We will use permutation multiplication. And how does it work? So if we have row sub 0 and row sub 1, so we will just get the double line notation of row sub 0 and row sub 1. So we always start to get this. So this is the result now. To get this, what we do is to start on the right side. So we will start on row sub 1. So 1 is to 8, 8 is to 8. That's why we have 8 here. And then 2 is to 1, and 1 is to 1. That's why we have 2 is to 1 here. And then 3 is to 2, and 2 is to 2. That's why we have 3 is to 2. And then 4 is to 3, 3 is to 3. That's why we have 4 is to 3. And then we have 5 is to 4, and then 4 is to 4. That's why we have 5 is to 4. And we have 6 is to 5, and 5 is to 5. That's why we have 6 is to 5. Then 7 is to 6, and 6 is to 6. That's why we have 7 is to 6. And then 8 is to 7, and 7 is to 7. That's why we have 8 is to 7. So this double line notation is row sub 1. As you can see here, they are the same. So row sub 0 and row sub 1 is row sub 1. That's how we get the elements in permutation multiplication. So to better understand, let's have another example. If we have row sub 1 and the row sub 1, so basically, unahin lang natin yung right side. 1 is to 8. To get this, unahin lang natin yung right side. No? So 1 is to 8, 8 is to 7. That's why we have 1 is to 7. 2 is to 1, 1 is to 8. That's why we have 2 is to 8. 3 is to 2, 2 is to 1. That's why we have 3 is to 1. And then 4 is to 3, 3 is to 2. That's why we have 4 is to 2. 5 is to 4, 4 is to 3. That's why we have 5 is to 3. And then 6 is to 5, 5 is to 4. That's why we have 6 is to 4. And then 7 is to 6, 6 is to 5. That's why we have 7 is to 5. And then 8 is to 7, 7 is to 8, 7 is to 6 rather. That's why we have 8 is to 6. So this double line notation is similar to, is equal to row sub 2. That's why row sub 1 and row sub 1 is row sub 2. Another example, we have row sub 2 and row sub 1. So start on the right side. So this is row sub 1, this is row sub 2. So this is the result. So to get the result, start from the right side or set row sub 1. So 1 is to 8, 8 is to 6. That's why we have 1 is to 6. And then 2 is to 1, 1 is to 7. That's why we have 2 is to 7. 3 is to 2, and we have 2 is to 8 here. That's why we have 3 is to 8. 4 is to 3, and 3 is to 1. That's why we have 4 is to 1. 5 is to 4, 4 is to 2. That's why we have 5 is to 2. And then 6 is to 5, 5 is to 3. That's why we have 6 is to 3. And then 7 is to 6, and 6 is to 4. That's why we have 7 is to 4. And then 8 is to 7. That's why we have, nope, 8 is to 7. 7 is to 5. That's why we have 8 is to 5. And this double line notation is equal to row sub 3. So you can see here. That's why row sub 2 and row sub 1, or the result of permutation multiplication of row sub 2 and row sub 1 is row sub 3. So we'll just continue that or let's have another example to better understand. So this is row sub 3 and row sub 1. Start on row sub 1 or right side to get the result. So row sub 8 is 8 is to 5. That's why we have 1 is to 5. So 2 is to 1 here, and 1 is to 6. That's why we get 2 is to 6. 3 is to 2. 2 is to 7. That's why we have 3 is to 7. 4 is to 3. And then 3 is to 8. That's why we have 4 is to 8. And then 5 is to 4. 4 is to 1. That's why we have 5 is to 1. And then 6 is to 5. And 5 is to 2. That's why we have 6 is to 2. 7 is to 6. And 6 is to 3. That's why we have 6 or 7 is to 3 here. And then 8 is to 7. And 7 is to 4. And this double line notation equal to row sub 4. So row sub 3 and row sub 1 is row sub 4. So we're just going to do the same process to get all the elements of permutation multiplication, and we will have this result. Now, as we can see, all the resulting elements in permutation multiplication are closed, no? Or the elements are also in the set. That's why we conclude that it is closed under permutation multiplication. Next, so this is the original table, and this is the table after 180 degrees rotation. And next thing that we need to do is to interchange its rows. So we will interchange the rows of the rotated table to make it symmetric to the original table. So the rows that we are going to interchange is row sub 1 to row sub 7, and then row sub 2 to row sub 6, and row sub 3 to row sub 5, and mu sub 1 to mu sub 7, mu sub 2 to mu sub 6, and mu sub 3 to mu sub 5. So this is the result after interchanging the rows. And as we can see, the structure of the resulting table is symmetric to the original. And we can say that it is associative under permutation multiplication. Now, next is the identity element. So as we can see here, there is a row that matches the outer top row. So this is the outer top row, and this is the row that matches it. And we also have a column that matches the outer left column. So their intersection is the identity element. So the identity element is row sub 0. So we can conclude that there is an existence of identity element. And lastly, so for the inverse elements, we can see that the identity element appear in each row and in each column. So each element have an inverse. So the inverse of row sub 0 is row sub 0. The inverse of row sub 1 is row sub 7. The inverse of row sub 2 is row sub 6. The inverse of row sub 3 is row sub 5. The inverse of row sub 4 is row sub 4. The inverse of row sub 5 is row sub 6, row sub 3. The inverse of row sub 6 is row sub 2. The inverse of row sub 7 is row sub 1. And the inverse of mu sub 1, mu sub 2, mu sub 3, mu sub 4, mu sub 5, mu sub 6, mu sub 7, and mu sub 8 is itself. So finally, we can conclude that there is an existence of inverse elements. So this results from the closure, associativity, identity, and inverse. We can say that the set of moves in our geometric model is a group under, or forms a group under permutation multiplication. So that's it for this presentation. Follow for part 6.